All right, let's wrap up energy by solving a whole mess of examples. Now, before we begin, remember a couple of things. You need to define your system because your system will determine what types of energy you have. Remember, an object by itself only has kinetic energy, and an object that you include the Earth with can have potential energy, and an object that you include a spring with can have spring potential energy. Otherwise, gravity and springs are external forces that will do work. Now, also decide how many forces are acting on the object and which ones are doing work, only the external ones, remember, and decide what types of energies you have at the different critical locations that you're interested in. And then, and only then, should you set up your conservation of energy equation. In the following examples, what we're going to do is I'm going to show you the question, we're going to talk about it a little bit, and then I'm going to show you the answer and discuss it and maybe have an add-on question. If at any time you have some issues with it, just pause the video and take a closer look at it if I'm moving too fast. All right, in this particular example, we have two baseballs that are thrown from the edge of a cliff at the same velocity. One's thrown straight up, one's thrown straight horizontal. Which ball will be traveling the fastest when it lands at the bottom of the cliff? All right, so what's our system? I'm going to include the baseball and the Earth, so I have both kinetic and gravitational potential energy. So since gravity is the only force on the ball, then I don't have any external work. So I should have conservation of energy where the initial energy equals the final energy with no work involved. So at the top, they both have kinetic, the same amount of kinetic. They both have potential, the same amount of potential. And at the bottom, they land at the same height. So I'm going to call that my zero height. So at the bottom, they shouldn't have any potential at all. So all of the same energy they begin with should equal the same energy at the bottom. So they should have the same kinetic energy at the bottom, which means they're going the same speed. Excellent. All right, next question. We have three identical crates that slide down 3-meter tall ramps of different shapes as shown in the figure. Assume there is no friction between the crate and the ramp. Rank the speeds of the crates at the bottom of the ramps from greatest to least. Okay, what should our system be? Well, it's change in height again, right? So I'm going to include the Earth in my system along with the box so that I can have gravitational potential energy and kinetic energy. They're all starting from rest, so they all should have the same exact gravitational potential energy since they all have the same height, and they're all identical, so they all have the same mass. They all slide to the bottom. There's no friction, so there's no negative work done. And so at the bottom, they should have the same kinetic energy. So therefore, they should all be going the same speed, which is kind of crazy because you wouldn't expect that, right? You would expect this one to be going faster. Now, why do we expect that? Because what happens is in the real world, there's friction. So if we had these three slide down and they all have the same coefficient of friction, which one's going to go fastest? Well, this one will. And the reason why is because remember, friction will be in the opposite direction we're moving. So therefore, we're going to have negative work. It's going to take energy away. And the larger the friction is, the more negative work there will be. So if you look at ramp C, the normal force is going to be the biggest because the perpendicular part of the gravity will be the biggest in C. So therefore, the friction force will be the biggest, because remember, friction force equals mu times force normal. In case B, over here, the normal force is going to be less, because we're at such a steep angle, the perpendicular part of the gravity is much less, so there'll be less friction. So in the real world, where there's friction, B goes the fastest, C goes the slowest at the bottom, because there'll be more negative work done in case C. All right, here we have a roller coaster car that starts from point A at rest. It launches at an angle at point B. How high will the car go? Will it go higher, lower, or the same height that it started at? Okay, think about that for a second. All right, what's our system? I'm going to have cart, and I'm going to have gravity, right? So I have kinetic and potential. So at the beginning, we start with only potential. If I call this lowest point down here 0, then it has its greatest kinetic right here. It has lost some kinetic here as it gained potential, and then it launches into the air. but this is launched at an angle. So it's going to take a path of a parabolic arc. So at the top of that arc, it's going to still have some kinetic energy. And because it has the horizontal component of the kinetic energy, horizontal component of the velocity, which leaves it with some kinetic energy at the top. So conservation of energy, there's still some kinetic left. It can't go as high as it started because it was all potential here. It'd have to be all potential. So how could we launch this car? Is there a way to launch the car to get it back to the same height? Well, we have to launch it in such a way so that it won't have any kinetic left. So if we launch it straight up, then it would go all the way up, stop with no kinetic, and then it must be back at the same height. Okay, next problem. Jane is having fun with a lion at the top of a cliff. As seen in the figure, Tarzan feels left out. He wants to swing over to Jane, but his cliff is only 12 meters tall, so he's 4 meters short. So he's going to run and then swing up to Jane. How fast is he going to have to run? All right, so I want you to pause the video on this one. I want you to set this one up, and then we'll go through the answer. Ready, set? Pause the video. Okay, here's our answer. Tarzan starts with some kinetic energy to convert extra into potential energy. So down here, I'm going to call down here my zero height, okay? And so he doesn't start with enough potential to get over here, so he has to have some kinetic. So he has kinetic and potential. And then there's no work done. Now, what are the forces acting on Tarzan? There's gravity. When he swings across, there's going to be gravity and there's going to be tension. But tension is always going to be perpendicular to the way he's traveling, like in a pendulum. So therefore, it won't be doing any work. So the work is zero. Then at the end, he's going to have only potential. He just needs enough to get to where Jane is. So if we solve all of this, you'll notice that the mass of Tarzan cancels out, and we'll end up with a velocity of 8.9 meters per second. That's actually pretty fast that he would have to run to get there. Okay, how about this? What if Jane grabs onto Tarzan and they swing back? What speed will they be going? So he swings all the way up here. He's at rest. She grabs onto him and they swing back. How fast will they be going then? Well, the mass has changed, right? But it's the same equations. We're just working it in reverse. They're going to start with potential energy. They're going to end up over here with some potential energy and kinetic. And the mass, again, is going to cancel out. So when they reach back over here, they're still going to be going the same speed that Tarzan started with when he ran to get to her in the first place. Okay, in this example, we have a skydiver that's falling 100 meters after pulling their parachute. I'm sorry. The skydiver falls 100 meters before pulling their parachute. See the figure. Calculate the speed of the skydiver just before they open their parachute if there's no resistance, and then recalculate it if there is air resistance of 200 newtons. Okay, so what's our system? Our system would be, how about skydiver and Earth? So we're starting with potential energy here. We're having kinetic energy here. And I'm going to call this my zero height down here. So we should have potential turning into kinetic. If there's no air resistance, then there should be no work done because gravity is included inside of our system. So we would get potential turns into kinetic, and they'd be going 44 meters per second. Notice their mass cancels out. Now, what if there's air resistance? If there's air resistance, the air resistance would be upward, and the skydiver is moving downward. So that would be negative work. And so we would lose some of our potential energy before it can turn into kinetic, and so we would be going slower, only 38 meters per second. Now, what height does the skydiver have to fall from to double their velocity? If you want to double the velocity, do you have to double the height? Notice that the height is proportional to v squared. So if you want to double the velocity, that's 2 squared. You need 4 times the height to get to twice the velocity. Now, if you have air resistance, it's even worse. If you have this part that's subtracted off, so you'd have to actually go even higher in order to double your velocity. Hey, another quick thing about this equation, you can see why something that has a larger mass would have a greater final velocity. So in this equation right here, in the real world, when we drop things, things that are lighter tend to be going slower when they hit the ground. Why is that? It's because for the same air resistance, they have more initial energy to begin with. And so they'll end up with more kinetic at the bottom because the mass doesn't cancel out when there's negative work done by friction or air resistance in this case. So that's why in the real world, when we drop a cannonball, we drop a ping pong ball, the cannonball will be going faster at the bottom because the air resistance has less effect. It takes less away from its original energy, because its original energy was much larger, so the amount that gets taken off doesn't affect it as much as it does for a ping pong ball. All right, our next example. A fire traps a person on a roof. The fire department puts out a trampoline with a spring constant for the man to jump onto. What is the maximum distance the trampoline stretches while saving the man's life? Okay, I want you to pause the video, decide what your system is, set it up, and then solve the equation. Did you get 2.1 meters? So if you choose the system that is the person, the earth, and the trampoline, spring, right? Then we should have gravitational potential energy over here where we start, and we should have, when we stop at the bottom, we should have only spring potential energy. And there should be no work done because our outside forces are only from gravity and the spring force of the trampoline. So there's no external work done, and so here's our answer. Now, what height will the trampoline launch the man to? Because this is a spring. So now he has all this spring potential energy after he's stretched the trampoline. Well, that energy will just turn right back into potential, right? And launch the person back up to the original height. This is why we don't use a trampoline to save people when they jump out of a building. We use something that won't snap back, that will turn that energy into heat, dissipate the energy. Okay? That's why they catch them in a blanket or something. Next example, another spring. A spring with a spring constant of 650 newtons per meter is compressed 4.6 meters and used to launch a clown at a circus, as shown in the figure. How high will the clown go? All right, how about a system of clown, spring, earth? We're going to start down here with spring potential energy. We're going to end up here with only gravitational potential energy because they're going to stop. And so the spring turns into gravitational, and we end up with a height of 12 meters. Okay, what height will the clown fly to if we double the compression of the spring? So what if we smash the spring down instead of 4.6 meters, we do it twice that amount? How high will the clown go? Well, in our equation right here, we can see that the spring compression, x squared, is related to the height. So if we double the compression, 2 squared is 4, so they'll go 4 times as high. Okay, now let's talk about energy bar charts. Okay, and let's use this example to kind of remind us what energy bar charts are. It's a way to visualize what the energy is so that it's sometimes a little bit easier for us to understand. And it's likely that these will show up on the AP exam as well. So here we have a roller coaster car starting at rest. It has a mass of 51 kilograms. It starts at a height of 80 meters. It's going to roll down here, and here's the bottom, and then part C is up a little hill, D is the top of the loop, and E is at the end. Okay, so let's say we have a frictionless roller coaster of science. So what will our energy bar chart look like at these points? Well, here's our answer. So we have our system will be roller coaster car and earth, and it's frictionless, so we don't have to worry about negative work done by friction. The normal force, remember, is perpendicular to the way the car is moving, so it won't be doing any work. So we should have conservation of energy, and we should have the same amount of energy all the way across. At the beginning, we have only gravitational potential. If you do the math, it's around 40,000 joules, and no kinetic. When we're at the bottom, we have no more potential, so it's all kinetic. At this hill here, we're halfway back to where we were before, so we should have half the potential, and the other half should be kinetic. at the top of D here, at the top of the loop, we're higher than halfway back up, so we should have more potential energy than kinetic. And then at the end, it's all back into kinetic. So here's an example. A box starts from rest and is launched up a ramp as shown. So there's a spring that's compressed a 0.4 of a meter. There's a spring constant, there's the mass, and it's launched and goes up this ramp and will eventually stop because it only has so much energy. So construct an energy bar chart for the box, spring, earth system for these 3 points. Calculate the speed of point B and what's the maximum height that this box will reach. All right, I'd like for you to pause the video, work that out, and then we'll check your answer. Please pause the video. All right, here's our answer. At the beginning, we have nothing but spring potential energy. And then at point B, if we call this height 0, I'm assuming you all call that 0, then we have no gravitational and all the spring turns into kinetic energy. And then all the kinetic energy turns into gravitational potential energy at the end. So at the beginning, all the energy at A is spring potential, which is 1/2 kx squared, which is 80 joules. That 80 joules equal the kinetic we have over here. And so if we plug that in, we end up with the velocity being 5.7 meters per second. And then, since the energy here equals energy there, 80, I just plug that in over here for C, and that all turns into potential, and we end up with a height of 1.6 meters. Uh-oh, now we have friction. The box still starting from rest and launched up the ramp. Okay, how does this change your energy bar chart? And how does it change our answers? So before we do anything, what's this going to do? Now the normal force doesn't do any work because it's perpendicular to the way it's moving. But friction is in the opposite direction we're moving, so that will be negative work. So this is going to have a negative work taking energy away between points A and B. But between B and C, the energy is still the same. Well, conserved between B and C. So the energy that we're left with at B equals the energy we have at C. So redraw your energy bar chart and resolve your problem. It's not that hard. Okay, what we end up with is this. From A to B, we have a new term. We have work done between A and B. And that's force of friction times this distance of the friction times cosine theta. But the cosine theta is -1 because they're in opposite directions, so theta is 180. So here's how I figured out what the frictional force is. It's mu mg. Plug in all of this stuff, and we end up with the velocity is less than it was the last time. It's only 4.2 meters per second. In our energy bar chart, you can see I start with spring potential, but there is negative work done. And so this bar is less than the original by this amount. But then from here to here, we end up with the energy still remaining the same. So I just plug those in, and I end up with 0.92 meters. So not as high as it was before. I think it went to 1.6 the first time. Okay, now let's talk about rotational kinetic energy. Remember to take into account the kinetic energy of rotation. Sometimes students forget that. One of the critical things about rotation for like if it's rolling, it requires friction is required to make something roll. So if I have a ball and there's no friction, it'll just slide. But there has to be friction for it to roll, okay? However, if it's rolling without slipping, then that is static friction. And if it's static friction, it doesn't do any work because the force does not move the object through a displacement. Okay? This is really critical. Things that roll without any slippage or slipping, the mechanical energy remains constant. So here's an example. So we're going to compare these two examples. We have a ball starting at rest at the top, and friction causes it to roll without slipping, right? So we start with gravitational potential energy for our ball earth system. And then there's no work done because it's rolling without slipping. and the normal force is perpendicular to the way it's going, so no work done. At the bottom, we have translational kinetic energy and we have rotational kinetic energy. These two bars must equal what we started with potential energy at the beginning. All right? Now, what if there's no friction? It's just going to slide straight down. With no friction, there's no rotational kinetic, and so all of the energy turns into translational kinetic, and it will be going faster at the bottom. Notice that both of these at the bottom have the same energy as at the beginning. So they have the same exact total energy at the bottom. But the one that slides, it's all translational, so it's translating faster, so higher velocity. So here, a block of ice slides down a ramp without friction, and a sphere rolls down without slipping, as seen in the figure below. Assume the ramps start the same height, blah, blah, blah. Which wins in a race to the bottom? Okay, well, we just talked about this. They have the same potential energy. At the bottom, they'll have the same energy since there's no losses due to work. And so this one's all translational, so the block of ice gets to the bottom fastest, but they both have the same energy at the bottom. Okay, now, what if the spheres or objects have a different rotational inertia? So in this case, we have a solid sphere and a hollow sphere. Start from identical ramps. They both roll down to the bottom. Which one wins the race? All right, there's an easy way to think about this and a harder way to calculate it. So the easy way to think about it is that the hollow sphere has 2/3 mr squared, and the solid sphere has 2/5 mr squared. The solid sphere has less total inertia. So therefore, since it has less inertia, it's easier for it to roll, so it will start up faster and it'll get down to the bottom quicker and have a higher velocity. Now, if we do this the hard way, with equations, we can prove this. So both of them start at the top with mg delta y, assuming the bottom is 0 again, and our system is the sphere and the Earth. At the bottom, they're going to have kinetic, translational, and kinetic rotational. Now, for the solid sphere, we'll plug in 2/5 for I, and remember that omega equals V over R. So we get V over R, and that's squared. When we do all this math, we end up with the solid sphere's velocity as square root of 10/7 g delta y. We repeat this and plug in instead the hollow sphere in here with 2/3, we get a different number. We get 6/5. Notice that 10/7 is larger than 6/5. So the solid sphere wins because it has a higher velocity at the bottom, which is what we predicted because it has a lower rotational inertia and it's easier for it to spin. Okay, now, what about the opposite direction? We have a disc and a hoop that are rolling at the same rate and they encounter a ramp. Both roll up without slipping and they both stop at the top. Which one rolls higher? Okay. For a system that includes the hoop or disc and the Earth, then we'll have rotational and translational kinetic energy at the beginning, and at the end we'll have only gravitational potential. Once you notice that both of them stop, okay? Since both of them stop, whichever one started, that means they only have potential energy at the end. So whichever one started with the most energy, it will go higher because it's all converting into gravitational potential. So a disk, if you remember, is 1/2 mr squared, and a hoop is mr squared. So it has twice as much rotational inertia. So what we end up with is, since the hoop has more rotational inertia, it'll have more rotational kinetic energy at the beginning because they both have the same velocity and the same translational kinetic energy. That means the hoop will go higher because it has more total energy for translating and rotating at the same rate. A ball starts from rest at the top of a curved ramp and rolls without slipping. It launches straight upward at the bottom of the ramp as seen in the figure. Will the ball go higher then? where it started, the same height, or will it go lower? Justify your answer. It's a trick question. See if you can get it. What's your prediction? Be very careful with this one. So remember when we had the car coming down here and going straight up, we said that if we launched it straight up, it would go to the same height. Now that's true for a translating only object, but this object has translational and rotational kinetic energy. When it leaves the ramp, it's moving and rolling. So when it's going up in the air, it will eventually stop going up, but some of its energy is trapped in rotational kinetic energy, and it cannot convert it back into kinetic energy. I'm sorry, into potential energy to get back to the same height. So it's going to end up back here under where it started because it's going to have potential energy and still some rotational kinetic energy when it gets to the top. All right, everybody, that's our very quick review of energy with a whole mess of problems. I want you to remember on the AP test, always try energy first, because if you can solve it that way, it's the easiest way to solve the problem and to explain it usually as well. All right, that's the last of our mechanics review videos. So you should be ready for the test. All right, good luck. Bye.